Hello, my dear students, and welcome back. Exams are just around the corner, I know, but don't you worry. Today, we're going to crack one of the most interesting chapters in your entire textbook. We're not just going to study physics, we're going to solve a mystery. Chalo, let's begin our investigation into the dual nature of radiation and matter.
So here's our plan for today. First up, we'll figure out why electrons need an energy boost to escape from a metal. Then, we'll dive into the big mystery, the photoelectric effect. After that, we'll see why the old wave theory completely failed to explain it. Then comes our hero, Einstein, with his brilliant idea of photons. And finally, a mind-blown twist. Matter has waves too. Let's get right into it. Okay, first things first. We need to understand the scene of the crime, which is basically a metal surface. So how do we get a tiny little electron to leave its cozy home inside a piece of metal? Well, you can't just ask it nicely. It's kind of locked in there. Think of it like this, beta. The metal is like a big city, and the electron wants to get out onto the highway of freedom. But to pass the toll booth at the city exit, it needs to pay a toll tax. This minimum energy, this toll tax, is what we call the work function. And just like the toll is different for different highways, every metal has its own unique work function. Simple, right? All right, now for the really strange part, the mystery that puzzled the best scientists for years and years, the photoelectric effect. We're going to look at all the clues from the experiment, so pay close attention, my little detectives. So here's our experimental setup. Imagine this is our crime scene. We've got two metal plates inside a vacuum tube. Light shines on one plate, called the emitter, and then something mysterious happens. Electrons jump from that plate to the other one, creating a current in the circuit. But how? Why? Let's check out the first clue. Clue number one is pretty straightforward. Scientists noticed that when they used a brighter light, a more intense light, they got a bigger current. It's kind of logical, right? It's like the more intense the light, the more electrons get knocked out every second. Simple enough. And this graph, which you'll find right in your textbook, proves it. It's a perfect straight line. As the intensity of light goes up, the photoelectric current goes up right along with it. Seems pretty simple, doesn't it? But this is where the mystery gets really, really weird. Now here's where it gets strange. This is clue number two. You would think that a super bright light would blast the electrons out with more energy, right? Make them move faster? Well, it doesn't. The fastest electrons coming out had the exact same energy, no matter how bright the light was. That just didn't make any sense at all. And look, here's the proof right from the lab. This graph shows that for three different light intensities, I1, I2, and I3, the stopping potential, V0, is exactly the same. This stopping potential is what we use to measure the maximum energy of the electrons. So no matter how bright the light, the energy of the fastest electrons just didn't change. What was going on? So if brightness wasn't changing the energy, what was? Well, here comes clue number three. The energy of the electrons didn't depend on how bright the light was. It depended on the light's color, or to be more scientific, its frequency. And you can see it right here in this graph. As you increase the frequency of light, from nu1 to nu2 to nu3, you need a larger stopping potential to stop the electrons. That means higher frequency light, like blue or violet light, was giving the electrons a bigger energy kick. So let's quickly summarize our mystery. First, there's a minimum frequency needed. Below that, nothing happens. Second, the whole process is instantaneous, super fast. Third, making the light brighter gives you more electrons. And fourth, changing the light's color, its frequency, gives more energy to each electron. So who's the culprit? Let's look at the main suspect. Okay, so at the time, everyone thought light was a continuous wave, like a wave in the ocean. This was the famous wave theory, so naturally it was the prime suspect. But when scientists tried to explain the clues using this theory, well, it completely failed. The wave theory just couldn't explain anything. It predicted that a brighter light wave should have more energy and kick out more energetic electrons. But reality, brighter light just meant more electrons, not more energy. The theory also said any color should work if you just shine it long enough. But reality? There's a minimum frequency, and the effect is instant. The wave theory was wrong on every single point. It was a complete failure. So the case went cold. Nobody could figure it out. And then along came a young genius, a hero for our story, Albert Einstein. And with one brilliant idea, he was about to solve the entire mystery. Einstein said, forget about light being a continuous wave. What if light is actually made of tiny little packets of energy, little bullets of energy? He called these packets quanta, and we now call them photons. And this is his famous photoelectric equation. It's so beautiful and simple. It says that the maximum kinetic energy of the electron is just the energy it gets from one photon, which is h times nu, minus the toll tax it has to pay to escape, the work function. It's like a photon gives you 10 rupees, you pay a 2 rupee toll tax to leave the metal, and you run away with 8 rupees of energy. Simple. And just like that, everything made perfect sense. A brighter light? That just means more photon bullets are hitting the metal, knocking out more electrons. Solved! Why does energy depend on frequency? Because a high-frequency blue photon has more energy than a low-frequency red one. Solved! What about the minimum frequency? Well, if the photon doesn't have enough energy to pay the toll tax, the electron can't escape. Solved! And why is it so fast? Because it's a one-on-one collision between a photon and an electron. Instant! Case closed! Okay, let's put this to the test. Let's try a quick problem. This one is just like example 11.2 in your book. These questions pop up in exams all the time, Beta, so let's make sure we've got this. So at the threshold frequency, the photon has just enough energy to pay the toll tax with nothing left over. So we set the photon energy, h times nu naught, equal to the work function. We rearrange the formula to find the frequency. Then we just plug in the numbers. And listen, Beta, always remember to convert the work function from electron volts, or EV, into joules. That's super important. Do the calculation, and there's our answer. Easy peasy. Now, just when you think the story is over, there's one final, absolutely mind-blowing plot twist. So, Einstein proved that waves can act like particles. But that led to another crazy question. Could it work the other way around? Could particles also act like waves? This question was asked by a young physicist named Louis de Broglie. He thought, nature loves symmetry. If light can have this dual personality, this particle wave nature, then maybe matter can too. Maybe an electron isn't just a particle. Maybe it's also a wave. And he came up with this equation. The wavelengths of any object is just Planck's constant divided by its momentum. Now look at this. For a big object like a cricket ball, the wavelength is so ridiculously tiny, it's basically zero. We could never, ever see it. But for a tiny particle like an electron, its wavelength is actually measurable. It's about the same size as an X-ray. It's real. And that, my dear students, is the big takeaway. Everything in this universe, from light to electrons to even you and me, has a dual nature. We're all both particles and waves at the same time. So think about that. What are you right now? A particle or a wave? It's a beautiful idea, isn't it? Keep revising, keep asking questions, and you are going to do great in your exams. I'll see you in the next explainer.